Okay, good morning all. So in the previous lecture, we looked at an example of a machine which which performs a kind of a mathematical operation, that is it accepts only those strings the sum of whose individual symbols is a multiple of 3, right? So this is one such particular machine. Like this accepts only those strings whose sum is 0 mod 3. Yeah. So then we generalized this machine to build a group of machines or a generic machine. Did I cover this? This I didn't cover. Okay, fine. All right. Then okay. So let's build a generic machine which accepts strings the sum of whose symbols is a multiple of, say, some n. It can be 4, 5, 100, million, whatever it is. The previous example we saw is a particular machine which accepts only those strings the sum of whose symbols is a multiple of 3, a particular number 3. So this particular machine has 3 states and so on. What if I want to build a machine which accepts strings the sum of whose symbols is a multiple of 4 or a multiple of 5 or a multiple of 2578, something like that. So I want to generalize that such a machine, all right? But each of those machines will be different. In this particular case, this machine has 3 states. If my n is 4, it will have 4 states. If my n is 10, it will have 10 states. If my n is 1 million, it will have 1 million states. So I can't draw each and every diagram separately. So this particular generic machine can't be represented in the form of a diagram. It can be represented only mathematically. Okay, so we will represent that particular mathematical formulation of that machine now. So formal description of a generic machine or a group of machines. This can be thought of as one generic machine or a group of individual machines. That accepts those strings the sum of whose numerical symbols is 0 modulo n. I hope you remember the previous machine. So basically, what does this machine do? Whatever input you give, it goes to the state which is basically that particular number mod 3. Suppose if my input is 1, it goes to Q1. But what does it mean? 1, if I add 1, it's only one number. 1 is 1 mod 3. All right. But if I give 1, 1, that is 2. 2 is 2 mod 3. But if I add 1, 1, 1, that is 3. 3 mod 3 is 0. 3 is 0 mod 3. Right? So, or if I take 1 and 2, that is again 0 mod 3. Or if I take 1 to 1, then what will that be? That is 4. 4 when divided by 3, the remainder is 1. So it will be in Q1. Okay. So each state is indicating what is the remainder when you divide the entire sequence of symbols with 3, the sum of the sequence of symbols with 3. So if I give 1 to 1, it is 1 plus 2 plus 1, that is 4. 4 mod 3 will be 1. So it will finally end up in Q1. So if I have to accept only those symbols or those strings, the sum of whose symbols is 0 mod 3, it should end in Q0 because 0 should be the remainder, which means it should end in Q0. So Q0 is the only final state in this machine. Okay, so that's how this machine is designed. In between, if you get reset anywhere, then whatever is the previous sequence of strings, you can ignore all that. It will anyway end up in Q0. So irrespective of the previous sequence of symbols, whether they add up to a multiple of 3 or not, doesn't matter. You are anyway resetting the sum to 0. Now you only need to worry about the symbols after the last reset. Whether these symbols after the last reset, they add up to a multiple of 3 or not, that's the only thing you need to care about. Okay. Now what we are trying to do is we are trying to build a generic machine where instead of 3, we take any n. Okay. So let's build a machine, say mn, and it will have this particular machine mn will have qn, because for each n the number of states change. When the n is 3, you have 3 states. When n is 4, you will have 4 states. When n is 10, you will have 10 states. So for each n, qn will be different. But will sigma change? We are right now taking only same sigma. We will take only 0, 1, 2 and reset these 4 symbols. So this input alphabet will be same for all the machines, whatever n is. Okay. So sigma will be same. So there is no sigma n, but the transition function will be different. So delta n, and then start state will be same, Q0. No matter how many states you have, there is only one start state. So Q0. And no matter how many states you have, there is only one final state. What is that? Q0. Because we are interested in only those strings, the sum of whose symbols is a multiple of n, which means the remainder is always 0 for that particular n. So it should end up in Q0. Okay.
If we add more symbols to sigma 5, 6, will the number of states change or remain same?
It will change.
So why will it change? The remainders will remain same. Like if we add 4, 5, 6 also to this alphabet.
Yeah.
Then we plot a machine for 0 mod 3. The remainders will be same. It will be 0, 1, 2.
No, you are considering only 3. What if I consider 5? Oh, for 3. Okay.
If we increase the alphabet, if we add more symbols,
it won't change. This particular machine will have only 3 states. If you increase more symbols, you need not add more states. You will have more transition arrows. Like instead of like if I add 4, I will directly go from 0 to 1. And I will go from 1 to 2, 2 to 0, like that. That's all. So you can add any number of symbols to the alphabet, but the number of states will not change. But if n changes, the number of states will change. N means 3 in this case. Later you change it to 4, 5, 10, whatever. Then those many states you need. Okay, so Qn for n will be what? Q0, Q1 up to Qn minus 1. Right? Because in this previous example, it is Q0, Q1, Q2. N is 3, it stopped at 2. So when you have n, the states go from 0, 1, 2 up to n minus 1. Okay. And sigma is same. We are taking same sigma. All right. So now let's work out the transition function. So delta n qj 0. So some generic state qj, you have only 4 inputs. So for each input, where does qj go to? Qj on 0, qj on 1, qj on 2, and qj on reset. So what is this? What is this? what is this, and finally what is delta n qj on reset. So can someone tell me what is this? If you are in qj, if you get 0, where do you go to? You remain in qj because the sum is not changing. Qj is indicating the remainder when you divide the current sum with n. Assuming the current sum is j mod n, that's when you are in qj. If you are adding 0 to that, the sum is not changing, so it will still be j mod n, so you will still remain in qj, right? So delta n qj 0 will be qj. What about delta n qj 1? qj plus 1 mod n. It can't be just qj plus 1, because what if you are already at n minus 1 and now you add 1 to it? Now the output will be n, but you don't have qn. You stopped at qn minus 1, so you should cycle back. So you need to divide that. So like in this previous case, I am in q2. If I get 1, I have to go to q0. I don't go to q3. I don't have q3. So how do I go to q0? I say 3 mod 3. I'll get 0. Okay. So q j plus 1 mod n. All right. What about this qj2? Same thing, qj plus 2 mod n. What about qj reset? q0, wherever you are, the moment you press the reset button, the sum will be again reset to 0, so you will go to q0. That's it. This is the generic machine. Now given a particular n, you fill the values of n here and translate that to a diagram. That's all. Okay. Clear? Any doubts? Okay, fine. So let's move on. So here all I need to write is where j goes from 0 to n minus 1, because we are dealing with qj and the states go from 0 to n minus 1. That's it. So j goes from 0 to n minus 1. All right. So let's ignore this. Let me delete this. Okay. All right. So now let's move on to the next topic, that is regular languages. So what is a regular language? A language is called a regular language if some finite automaton recognizes it. All right, that's it. Simple definition. It is an indirect definition. A regular language is one. If a language is recognized by a finite automaton, it's called a regular language. That's it. We have a clear definition for a finite automaton. A regular language is in turn defined using a finite automaton. That's all. And I think I already gave you a particular example of regular language in terms of regular expressions earlier. Like for instance, So like I gave you this example where suppose you have a text which has many words related to fishing or fish. You have all kinds of words: fishing, fisheries, fisherman, just fish, right? Now suppose you have to match any of these words, say in a word file. What do you do? If I want to match fishing, I have to search fishing. If I want to match fisherman, I have to search fisherman. Like we do like this, right? So this will map or match only with the words fishing. Suppose if I search for fisheries, this will match only with the words fisheries. If I search for the word fisherman or fisherman, it will match only with those words. But suppose I want to match all the words starting with fish. I want to match fishing, fisheries, fisherman all in one go, rather than typing every possible variant separately, right? Then the only way for me is to use something called regular expressions. Okay, so how do I do that? Let me increase. So I type fish and then I say small letters or capital letters. Normally it will be small letters, but I'm just using both. This set of A to Z, any English alphabet, small or capital, occurring 0 or more times. What is the symbol for 0 or more times? Yeah, star. Now you see all the words are matching which start with fish. Fishing is matching, fishers is matching, fisheries is matching, fisherman, fishermen, all these are matching. Now I need not search separately for each of these words. Okay, this is possible because I am using a regular expression. Okay, so this regular expression is basically saying, okay, the first 4 letters should be fish, and then this expression in square brackets, A to Z, small letters, A to Z, capital letters, it is basically saying it is a set of letters out of which any one letter can come. All right, it's actually indicating one letter, but this one letter can come from this entire set. Now, the point is, from this set, any one letter can come 0 or more times. So now this entire set you are repeating 0 or more times. So until it encounters a letter, it keeps encountering a letter. It will keep matching until it encounters a non-letter, that is a space or a full stop or whatever. So that is where these are stopping, right? You see all these words, fishers, it stopped before space. Every word is stopping at the before space, right? So it stops at space. It will not match space and other letters because I gave only the English letters as my set. It will only look for the letters in that set. If space is part of that set, then it will match space also, but space is not part of that set, so it will stop at letters. All right, and it will also match all even non-meaningful words like this last word fish followed by something, because that's my rule. The way I gave the rule is like that. Any sequence of letters followed by fish, you match with that. That's all. Okay, so regular expressions are extremely powerful, and particularly for these kind of tasks, regular expressions are used. And any language can be represented using a regular expression is a regular language. This is another definition which I am giving. We will come to this definition later, but this is another definition. A regular language is one which can be represented using a regular expression. Okay. Other definition is a regular language is one which can be recognized by a finite automaton or a finite state machine. Okay, so this is the idea of a regular language. Okay, a regular expression by itself denotes an entire language. A regular expression does not denote one string. A regular expression denotes a set of strings, and this set of strings denotes a language. Okay, so expression may be one, but it is pointing to potentially infinite strings. It is pointing to an entire language, not one string. Okay, like this expression, it is pointing to all these words, not any one word. So all these words put together will give you the language. All right, so regular expression, an entire regular language can be compressed into a single regular expression, and vice versa. Okay, yeah.
It should have highlighted the words which start with fish, but it has highlighted some words which end with fish.
No, start with fish. I did not say there should be no letter before that. I just said start searching for fish. Okay, Suppose if I say there should be no letter before that, then it will be different. I didn't say that. It can start anywhere in the text, right? You see, the entire text is nothing but some sequence of symbols for the computer. According to your logic, it should not find the word fish except in the beginning of the file, right? Okay. So we will now investigate the properties of FSMs and RLs. What are FSMs? Finite state machines. Okay. So finite automata or finite state machines, both are same. And right now we are still discussing deterministic finite automata. We still didn't come to non-deterministic finite automata. So whenever I am referring to finite state machine, understand it as deterministic finite automata. Okay. This will enable us to develop a toolbox of techniques for designing automata to recognize regular languages and also to prove that certain other languages are non-regular. Okay, so we need some techniques to operate upon regular languages which help us in dealing with them or recognizing them, and also to say which languages are non-regular. Okay, so you'll understand that in a minute. So for that, we need to look at something called regular operations. So regular operations, to understand that, let me give you an analogy. Say in maths, so one we have maths and another, say we have theory of computation. In maths, what are the objects? What kind of objects do you deal with in mathematics? Yeah. Functions, yeah, functions, sets, numbers, right? So everything can be reduced to sets, actually. That's true. So let's just take simple, whenever we say maths, what comes to our mind? Numbers. Whereas in theory of computation, the basic objects are languages. And in maths, what are the tools that we have to deal with numbers? Yeah, we have operations for manipulating them, for manipulating numbers. like addition, subtraction, multiplication, etc. Right? In theory of computation, similarly, we have specific operations for manipulating languages. So these are union, concatenation, star, etc. So we'll look at them. So let's define them. For regular languages, for regular languages, we define three operations called regular operations. They are union, concatenation, and star. So union, say A union B, that means set of X such that X belongs to A or X belongs to B. Similarly, concatenation represented as A dot B, that is set of XY such that X belongs to A and Y belongs to B. All right. Now star, that is A star, is set of x1, x2, x3 and so on up to xn such that n greater than or equal to 0 and each xi belongs to A. So let me give you an example. So let's assume my alphabet set is the entire English alphabet set, A, B, C, D up to Z. Okay. Now say I have two sets A and B, where A has two strings, red, blue, and B has two strings, ball and pen. Now, what is A union B? A union B is all these four words, right? Red, blue, ball and pen. What will be A dot B? Yeah. Yeah. Red ball, red pen, blue pen. Okay. Will also, do we get ball red, ball blue? No, because order is important. A dot B is different from B dot A. Okay. Red ball, red pen, blue ball, blue pen. Okay.
A cross B and A dot B are same.
Yes, in the sense that in A cross B, you write it as a tuple. In the sense, it's a slight difference basically. Like A cross B is what? You will write it as red ball, this is one tuple, then red pen, this is another tuple, then blue ball, then blue pen, blue comma pen, and so on, right? So this is A cross B. Here we are not dealing with, we are dealing with sets, but we don't want to treat them as sets as such. We want to treat them as some special sets. We are dealing with strings. We are dealing with languages. We want to get a language with larger strings. A and B, they are languages. And A has some strings, B has some strings. A dot B is a new language with larger strings. Red ball, red pen. This is a larger string than individual words, red or pen or ball. Okay, so this is possible because I am treating them as languages and I am defining special operations on special sets called languages. Concatenation is slightly different from cross product. For that reason, if I do cross product, I'll get tuples. I won't get larger strings. That's why. Okay. Yes, we can concatenate with the epsilon also, but we will get back the same string. Epsilon concatenated with anything is that string itself. Yeah. Okay, now what will be A star? You see, both union and concatenation are binary operations. They need two inputs. A star is a unary operation. It needs only one input. Okay.
Just a language, red, blue,
It is A.
A star.
So basically you're saying A star is nothing but A.
No, like red, blue is together.
Acha. So you're saying it will be red, blue. That's all.
Or it can just be red. Or blue, red.
It could be epsilon.
Okay.
Epsilon red.
Okay. Epsilon. Huh? 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 Hmm. Okay. Red, red, blue, and so on. What about red, red? Okay.
Epsilon union AI AJ and AI AJs are from
Hmm. Yeah, you are close to the answer, but you are not able to formulate it properly in a mathematical way. You remember how we built sigma star? Yeah, that is one way. A star, B star, whole star, assuming sigma has only A comma B as its letters. But suppose you don't know what sigma has. So in terms of sigma, how do we define sigma star? Epsilon union sigma plus. How do you define sigma plus? Yeah, sigma power 1 plus sigma square plus sigma cube and so on, right? Same thing here. So let me, I'll come back to this. So again, let me start step by step. What is a power 0? Epsilon, anything power 0, any set power 0, particularly when we are dealing with languages, will be epsilon. That's all. Because a power 0 means what? Strings of length 0. Okay, actually, it's not exactly strings of length 0. You will understand why. For sigma, it will hold exactly like that. But for languages, it will not hold. You see, sigma powers are powers of alphabet set. A powers are powers of language set. Both are different, but both will work almost exactly in the same way. The logic is same. Okay, so what will a power 1 be? A power 1 is nothing but a. This is again like mathematics. X power 1 is x. Same thing here. A power 1 is a. Sigma power 1 is sigma. This is true for alphabet set. This is true for language set. This is true for a number also, right? That is red and blue. What is a square? Yeah. So a square is nothing but a dot a. It is nothing but a dot a, right? So that is red, 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 blue. Okay. Right? In when we were dealing with sigma square, what did we say? We said all strings of length 2. Right? Sigma cube means all strings of length 3. Why? Because we are concatenating sigma with itself. Even there, we are actually concatenating. Sigma dot sigma will be strings of length 2 because in sigma, each character is of length 1. So when you put length 1 character with itself 2 times, you will get a string of length 2. When you put length 1 character with itself 3 times, you will get strings of length 3. So there we could say, we could speak of sigma cube, sigma square in terms of strings length because we know each character is 1 of length 1. Here also, if we assume each word is of length 1, suppose this is unit length, again this is unit length. Even here I can say a square is set of all strings of length 2. I'm not getting inside red, inside blue. I'm just taking red as 1 unit. I'm just taking blue as 1 unit. So a square is strings of length 2 in the sense 2 units. Red, 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 blue, blue, red, blue, blue, like that. Okay? And so on. Okay, let me move on. Similarly, yeah.
The language set A doesn't have epsilon in it, so how can we say that epsilon A equals 0 into epsilon, right? If we have sigma, it has symbols. If we do not choose any symbol, that we will get an epsilon string.
Yes.
But here A is not an alphabet; it's a language.
When you here also you are concatenating 0 strings. You are concatenating no strings. See, you can concatenate letters to form a string, or you can concatenate strings to form a larger string.
Not there in the set. The set has red and blue. The no string is not there inside. How can we concatenate that?
No character is not there in sigma also. I understood your point. Basically, sigma is alphabet set, whereas A is language set. Okay, but the logic is same. You can concatenate one or more letters to form a string. Similarly, you can concatenate one or more strings to form a larger string. Okay. Now, when I am concatenating, I am making a choice. In sigma, I am choosing which letters to pick up, which letters not to pick up. If I choose no letters, I will be left with an empty string. Similarly, in this case, I am choosing which strings to pick up, which strings not to pick up. If I choose to not choose any string, I am left with an empty string. When I choose one or more strings, I am left with a larger string. When I choose no strings, I am left with an empty string.
Now we are choosing symbol that make a string. Here we are choosing strings. So if we choose this no character, that will make an empty string. Here,
Not no character, no string. In this case, no string.
in sigma, epsilon is we define epsilon as when we choose no string, no character from sigma.
That is not definition. That is not definition. That is the outcome. Sigma is empty string. Okay. Sigma is not defined as that which you get by choosing no character. That's not the definition of sigma. Sigma is an empty string. In the case, not sigma, I'm sorry, epsilon. Epsilon. Epsilon is an empty string. Okay. That is the definition of epsilon. Its definition is not that it is that which is absence of any character. That is not the definition of sigma. Epsilon. It is the outcome of not choosing any character. In the case of sigma. In the case of a language, again epsilon is an outcome of not choosing any string, but still is an empty string. So the point is, empty string can be built by choosing 0 characters or by choosing 0 strings. That's all. Similarly, a cube is a dot a dot a, that is red red red, red red blue, red blue red, red blue blue, blue red red, blue red blue, blue blue red, blue blue blue. Okay, and so on. Right? A power 4, a power k, up to a power k, whatever it is. Okay. Now, so what is a star? That is nothing but a power 0 union a power 1 union a square, a cube, and so on. Right? So what is a power 0? Epsilon union red blue, red red, red blue, blue red, blue blue. Okay, should be union. Yeah, can someone close the door? And union this entire thing. So let me copy this. And so on. Union. So let me move this little left. Union. Dot, dot, dot. Okay. So here, this set will be epsilon, red, blue, red, red. So you can think of again these as strings of length 1, strings of length 0, strings of length 1, strings of length 2, and so on. So here length 1 means the entire word, the element in A. Each string, no matter what its length is, I am taking that entire string of length 1 as length 1. The string may have 10 or 100 characters, but I'm just taking that entire string as one element and one unit. And length 1, I'm just assuming. Okay. So here this length is not character length. This length is the unit length. The string is 1 unit, like that. Okay. So red, 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 blue, and so on. Okay. So this is my A star. All right. Can you tell me what is the relation between A and sigma, like mathematically? A is a language over sigma, or relation between any language over sigma. What is the mathematical relation? Yes, yeah. Yeah, you're right. A is a subset of sigma star. A is a subset of sigma star. Any language over sigma is a subset of sigma star because sigma star is the universal language that can be built over sigma. Every possible string you can think of that can be built out of sigma, that will be part of sigma star. So any language you build over sigma, that has to be a subset of sigma star. Either it is equal to that or it is a subset of that. Okay, like you see A B here. A has some two strings, red and blue. These are only two strings and this is one particular language. This is built over sigma, right? And B is another particular language built over sigma. These languages are just subsets of a much larger universal language that can be built over sigma, right? So for any language L over sigma, L is a subset of sigma star. Okay, and L star is nothing but all possible concatenations of all possible lengths over L. In the previous case, sigma star is all possible concatenations of all possible lengths over sigma. Here it is L star. L star is all possible concatenations of all possible lengths over L. Okay, so here concatenation is the crucial word. Okay, so this can also be represented as L power 0 union L power 1 union L squared and so on. Let me add one more. But what are these? L power 0 is epsilon, union L power 1 is L square is L dot L, and L cube is L concatenated with L concatenated with L, and so on. So what do we understand from this? So the star operation is built out of union and concatenation operations, right? So the star operation is built upon union and concatenation operations. Okay, but for all these three operations, what is the input and what is the output? Not for all three is the same, but the nature of the input and output, not strings, languages or language sets. Each of these operations, union and concatenation are binary operations. So they take two languages as input and return one language as output. A union B will give me one particular output. So A is a language, B is a language. I take two languages and perform their union and give one language as output. Similarly, A dot B, I take two languages as input and give one language as output. A star, I take one language as input and give some other language as output, a larger set. Okay, so all these operations have languages as inputs and outputs. That's the reason where in the previous table, when I showed the table, I said these are specific operations for manipulating languages. So their inputs and outputs are languages, whereas in mathematics, like numbers, their inputs and outputs are numbers, like addition, subtraction, etc. The inputs and outputs are numbers there, right? Here we are dealing with languages. We are performing these operations on languages. Yes, we can do concatenation on strings also, but the point is, that is fine. You can do concatenation on strings, but that is the what do I say? That is the resultant of concatenating two languages. You can, so basically you are boiling down concatenation of two languages into concatenation of strings. That is fine. But union you can't do with two strings, right? You have to take sets, right? So your point is fine, but we are dealing with concatenation of languages, and that is boiling down to concatenation of strings. This concatenation you understand from programming. Okay, but we are defining that particular concatenation is coming because we are taking some set of strings and some other set of strings, and we are taking one string from here and one string from here and just joining them like this. I can take only two strings at a time. I can do that also. That is also fine. But here we are discussing concatenation at set levels. Not important, but here we are discussing concatenation at set level. Okay. Yeah. So let's stop here.